So, hi everyone. Welcome to the third lecture of machine learning methods for atmosphere, ocean, and climate science. Maybe you're at this point saying that all we learn is, or we hear about is machine learning. What about atmosphere, ocean, and climate science? But hopefully, tomorrow's lecture would probably set things in context where we learn, where we see whatever we have learned be applied, and we see how these tools are being used for research out there. So today we will build on what we saw yesterday, and we will develop a different kind of neural net, which is called a convolutional neural net. Now, these neural nets are quite popularly used for image processing because they use a certain mathematical operation called a convolution, which allows extracting certain features from an image, from an input image. Now, we looked at artificial neural nets yesterday, and we had a typical benchmark data set of images. And what we did in order to train the model was that we took the image, which is a 2D object, sort of, right? And we transformed it into a one-dimensional vector. And then we used that as an input to train the model, and along with the associated output of what the digit was. So we achieved an accuracy of prediction skill of 97 something, which is not bad. But then to really go the next step and improve the prediction skill further to reach something more than 99% or so, ANNs might not do a good job. Mostly because, as you see here, a simple schematic consisting of 24 pixels. So they could be, so essentially if your vector is 24 by 1 after transformation, then the ANN doesn't really know the topography, the geometry of the image. All it sees is 24 pixels, and it somehow tries to learn the correlation between different indices of the input vector. So the vector, the 24 by 1 vector, could come from a 6 by 4 image or an 8 by 3 image, and the ANN has no clue about that, right? So convolutional neural networks try to solve this problem through an operation called convolution. Now, you have heard of convolutions in mathematics, where you have two functions, f and g, and you take convolution of those functions, which looks something like this: an integral from minus infinity to infinity as over the integrand tau. And it's not just a component by multiplication, but then the function g is translated in time in this variable. Now, the convolutions that are applied in CNNs are similar to this convolution. They're not exactly like this, but they are similar. And what essentially is being done is, instead of transforming the image to a vector, you start with the image, you do not transform it, you preserve its shape, and then you use a convolution operation to get a simplified depiction of the image through something called as filters, okay? And then you use certain filters. I'll try to make it clearer in a bit, but you use these certain filters, and then you go using these filters through the image, and then you create a simplified form of this image. And then you further reduce the dimension of the problem further through an operation called pooling. And then you have multiple such layers which further reduce the dimension of the problem. And then once you have this reduced 2D matrix representation of the image, you feed that into an artificial neural net, which we saw yesterday, okay? So CNNs kind of use ANNs, but then before using the ANNs to learn the appropriate weights, it uses a couple of operations for feature extraction from the image. So quite broadly, the steps involved in using CNNs and implementing them in PyTorch would involve the following pointers mentioned here. Firstly, a filter would be used to convolve through the input image by striding throughout all the pixels of the image, and it will create something called as a feature map, which would highlight the main key features of the image that if you have a dog or a cat, it's the ears or the nose or the eyes or the shape of their head that helps us determine what animal it is, right? So it's those features that define and help identify what exactly is in the image. The convolution, this operation captures that. And then finally, because even after you generate a reduced form of this image, you might have an image that could be large in size, right? So you kind of downsample that image using an operation called pooling. Now the pooling still outputs a 2D object, an image, not a vector, but it reduces the dimension of the problem significantly. And then the way you could do is choosing, okay, we'll look into this further, but there are different kinds of ways to downsample, either by taking a maximum over a certain domain or a minimum or an average. And then once you go through this pooling operation and multiple such convolution filtering operations, you feed your image by, again, reshaping it into a vector and feeding it to a ANN. Did I cover? Okay. How do I get rid of this? I guess we'll have to do with this. Okay, so let's see what a convolution exactly does. Now, consider this simple matrix, a 3x3 matrix, which is just consisting of 1x9, 1x9s. You have 9 pixels, so you have 9 objects, or 9 objects in this matrix. So it's essentially taking an average. So like suppose you have this image, right? This Super Mario image here, and you run this 3x3 matrix throughout this image. So whenever you do this, suppose you take a 3x3 matrix and you apply this operation here, what you're doing is, by applying this filter, you're taking the average over all the 9 pixels that coincide with where this filter is. So when you do this for the whole image, what you're getting is the image on the right, which is a sort of a blurred representation of what the initial image was. But it's still, just by looking at the right image, you can probably make out certain features, the hand, the face, the hat, and so on, right? So it does not destroy all the features, but it does average out the small scale features. So depending on what the filter is, right now we have an average filter that averages over the pixel. Depending on what the filter is, your output image would be different. Okay, so just for an example here, so suppose you have this kind of a filter that runs through this image. It does not destroy the whole image, but it kind of creates a blurred representation of this image. You can still figure out that there are buildings, there's water, and there's sort of a bridge there. So now the next step is kind of the question, what the optimal filter would be if you want to recognize the key features of an image. So the key objective of applying a CNN would be estimating what the filters are. However, let's take a step back and then kind of try to understand it the other way around. So suppose we have a given filter, which a 3x3 filter, which looks something like this, -1/2 in the first column, zeros in the second, half in the third column. And then you apply it to the image. So this is something called as a Pruitt filter. And if you apply it to this image of the cat, then you will kind of get a reduced version of the cat, which looks like this. So you can see that there's highlighting. It strongly highlights the features, the corners, the edges of the cat, of cat's ears, of cat's, whatever this is called, and the whiskers and so on. And if you kind of go back and think about what the filter is doing, it's taking the pixels in this column, it's taking the pixels in this column, and it's taking the difference of the pixels. So it's something like a derivative in the x direction. Okay, so wherever the horizontal derivative is strong, it's capturing those features. And similarly, if you take the transpose of this matrix, you will get a filter that captures the vertical gradients in the image. Now, similarly, there's another filter called a Sobel filter, which is similar to the Pruitt filter, but it's just the weightings are different, but it's essentially doing the same thing, taking the gradient and laying more emphasis in the central pixel. Similarly, there's a Laplacian filter, which, if you have seen or derivatives in the 2D space, then that's sorry, this is the Laplacian in the 2D space, I think. Yeah. So that's why it's called a Laplacian filter. Yeah. So if you apply this filter onto your image, then you get features which are, so this filter essentially takes into account really localized features which are not, spanning in either the x direction or the y direction, like the eyes. So if you apply this filter to the cat's eyes, you see that it's not highlighting the quasi-vertical, the almost vertical edges of the cat's ear anymore, but it's highlighting small features like the cat's eyes, like the sparkle in the cat's eyes, and then the whiskers, which are small scale features, and then they don't, they don't span throughout the vertical or the horizontal. So now a quick question. Suppose we have this kind of a filter and we run it through the image. What kind of effect do you think this will have on the image you get? Or what features will it focus on? Hmm? Central features as in? Sorry? Yeah, exactly. So so I hope the idea of a convolution is clear, but yeah, suppose you have an image, right? You have a big image consisting of many pixels. It could be a vortex image as well. It could be clouds. It could be waves. So you're taking a 3x3 filter. You are taking a component-wise multiplication of the filter with the original contents of the image, and then you are just taking the average of the individual products. Okay, and then you move it by a certain amount called the stride, and then you do this operation on and on until you get a reduced version of the image. Okay, so on. And now if you have just run along the diagonals, and then suppose your image is like a big X, then as you can see, it will capture the features here, and it will zero out the features that are not really an incline. So and so on. What you will get is a highlighted feature which will emphasize more on the oblique lines in the image. Okay. So so yeah, as I mentioned, now the filters, in this case, our filters were fixed, and we noted what the effect they have on the image when you convolve them throughout the whole image. Okay, but in CNNs, you don't have the filters prior. You determine what the optimal filters are by training your model on the data. So again, you can have different layers of such convolutions, and each layer has different set of filters. And depending on the problem, and depending on what features you expect to be in the input, you can, for instance, here have these. If you're using it for face detection, for instance, there would be high-level features, which are like the overall geometry of the face, or there would be mid-level features, which is like the eyes, the nose, and the lips, and so on. And then there are further small-level features like eyebrows or a mole, things like that. And different features, the different filters at different levels will capture different of these features. Now, as an example here, there's a feature map for clouds. So if you have an image of a cloud and you run it by a CNN, and then you look at how the input evolves after each convolution layer, so you get something like this. The first layer identifies the most obvious features present in the image, which is these wavy structures associated with these different phases of the clouds. I mean, there's patches where there's no clouds, there are patches where there are clouds, depending on the temperature. And the second layer, which builds on this first layer, is less interpretable, right? You can't really figure out what it means and how can you actually make a prediction based on this. And then the deeper you go into the neural net, the less of an interpretability you have of your input. And I mean, one way to see this is, of course, this is a problem. I agree. I mean, that we can't interpret the output is kind of a big issue, and people are working on that. But on some level, if you connect it to our understanding, we have eyes, we see clouds, and we see the most obvious features, which is associated with level 1 here. But then, as you think more and more deeper about what happens what happens when the eyes send the signal to your brain and how your brain interprets it, we don't clearly know that, right? And there might not be a clear structure in that. So yeah, I'm not trying to defend anything, but yeah, it's maybe in the future, we'll have a better way of interpreting all these lower dimensional signals that we cannot interpret now. So let's start with the coding part, and I've uploaded the notebook for today's lecture at this link here, this first link, and I've also converted the Jupyter notebooks into HTML pages, and I've uploaded it in the second link so that if you're not able to run the notebook on your laptop, you can at least look at the code. Okay, and it's a zip file, and you can download it from this link here, and hopefully that should help. So to summarize what we are trying to do is we'll start with the same data set, and we'll see if we use this new kind of method of to process the input, does it make a difference, and how much difference does it actually make? So we will look at the image and we'll define a set of filters. We'll start with the original image. We won't distort its shape, and then we'll define a set of filters. We'll see how we can do that in PyTorch, and then we'll go through this sequential process of applying convolutions, activations, and then pooling and reducing the dimension of the image, and then further applying another convolution, and then pooling again, and then ultimately feeding it to an artificial neural net. And sorry, just a quick pointer about yesterday. I'm sorry if you tried to run the Jupyter notebook, you must have gotten an error in the training step. So that's because the training function is returning 3 variables, but then in the next cell we were only capturing 2 variables. There was no provision to capture this initial skill variable. So I've corrected that now, and I've re-uploaded the corrected version. And if you can download it, or if you just add this into the function call, then that should also resolve the error. Sorry about that. I've also added some pointers or some notes here that you can, when you're trying to run the code yourself, you can just refer to. Now, is everyone able to find the notebook, download the notebook? Okay, just let me know if you're not able to, okay? So, okay, someone said yesterday I went too fast yesterday, and I had to because I felt we won't be able to finish it in time. So I'll try to go a bit slower today, and thankfully we have done most of the work yesterday, loading the data set, and then forming the ANN part of the problem. So we can actually afford to kind of slow down a bit today. So the first part, this cell, the initial cell is same, identical as yesterday, loading the necessary modules, the data loaders, and the relevant components to download the data set. Again, we are working on a CPU, and then I've reduced this set. I've erased a lot of comments that were there yesterday, so we only have the relevant function calls now and no other details. So you load the data set, the training set and the test set just as yesterday, and we are working on the MNIST data set again, and again the number of data points are 60,000, 10,000. So we don't have to worry a lot about this because we have seen this yesterday. Now batch size, again we start with a batch size of 40 for now. And yeah, we can try to just visualize our output randomly, and yeah, these are handwritten digits. Now, one important information it's good to know is how the convolution operation changes the geometry of image. I mean, as I mentioned, we still get a 2D image once we run the convolution by the image, but the dimension, the length and the breadth of the image might change. So suppose so this relation here, this codifies what exactly happens when you apply the convolution. So suppose your input image is of dimensions n in. Just assume a square for now, okay? Isotropy. So suppose you have your input dimensions n in, and your kernel size, that small window there, that's of size k by k. And then, just for the sake, you can sometimes apply a padding of zeros or any number you want, but mostly zeros. So you can kind of extend this image and just pad it with zeros. So you initially expand the dimension of this image, but then you add this padding so that you can get a more favorable output dimension once you apply the convolution. Because I guess it's easy to see that once you run this convolution, 3x3 convolution through a bigger picture, it will reduce the dimensions by a couple on both sides, because you don't have you have information, relevant 3x3 information here, but then you don't have, suppose this is your center associated with the 3x3 convolution, and you don't have information on the boundary. So you can kind of take care of that by padding, and once you add this padding, let the size of padding on each side be equal to p, and at every point of once you run this convolution through your image and then you move over to the next cell, it's up to you how many steps you want to take to go to the next cell. So okay, I have made a bad picture here, but so I'll make another square. So suppose now you have a 2x2 convolution, okay, 2x2 filter. So you'll start with the first top left corner, and then it's up to you if you want to kind of switch to the right next cell, which is this cell, this 2x2 cell here, or you can take a stride or a jump of 2 units, and then you can start by this cell, or you can have a stride of 3 units, and then you can directly start with this cell. So that's what the stride parameter decides, like how much of a jump you take before you choose the next cell to convolve with. Sorry? Yeah, 1 is a good number, I think, but as you'll see, for the pooling layer, it's usually 2. Or it depends on the size of the pooling layer, actually. So, yeah, I guess you have more information if you take smaller strides, but then if you have larger strides, then you're kind of losing on the information. So, yeah, start with the stride of 1, I would suggest. If anything, stride should be, bounded by the kernel width. Either way, because otherwise if you have your kernel here, and then if you take a bigger stride, then just imagine this image extends. So then you're kind of not accounting for the information here. It should always be bounded by the kernel width. Sorry, yeah. Sorry, again. There is an activation function. Oh, is it? So GALU is a variation of ReLU, so it doesn't matter much. I must have, yeah. Feel free to use ReLU. It shouldn't make that much of a difference. The only difference is this is your ReLU function, which is non-differentiable at 0. But then the GALU function kind of adds a Gaussian smoothing here so that it's differentiable at 0. Sorry? Oh, okay, yeah. So it's like, suppose let's take a very simple operation. So say you have a 3x3 grid, okay, and then your kernel is 2x2. So this is your kernel, and this is your image. Now you first run this through this box. You take the average, and that gives you the first element of your output image. And then you take a stride of 1, and then you compute the average over this box, and then you take a you set the value, you put the value here. Yeah. Now you have noticed that in doing so, you have reduced the size of the image. So earlier it was 3 by 3, but now it would be 2 by 2. But what if you want to, have the original size 3 by 3? So that can be resolved by having a padding of 0 here, so that your initial convolution actually starts from here, accounting for zeros. So then now you will have 1, 2, 3, 4. Okay, we ended up with more, but yeah. So basically, you get the idea, right? I mean, if you have a 3 by 3 cell and padding of yeah, we ended up with one more dimension in the image. If we added padding here and here, then we have 2 more dimensions. So it's a 4 by 4 image ultimately. But you get the idea, right? So let's see how we implement this in PyTorch. Okay. So just like we created the ANN module yesterday, we use the NN.module. We created the ANN class yesterday. We use the NN.module base class to create a CNN class for our neural net. And again, it has 2 key components. First is the initialization, and what your architecture looks like, and you initialize the model with the relevant weights and the filters. And then you have a forward step, which is used during training, during the forward pass. So what's happening here? Let's see. So we first define the convolution layer. Okay, so let's look at this command first. So this is the first convolution layer. We have another such convolution layer. So the first convolution layer is defined. So because we are working with a 2D image, we are using this 2D convolution layer. There are convolution layers, this 1D and 3D convolution layers available as well, the PyTorch library. So this 2D operation takes the following inputs. So the inputs would be the number of channels in your input image. So like as I mentioned yesterday, the color image are usually composed of 3 channels: red, blue, and green, and each individual channel emphasizes on different features of the image, and when you together put these 3 channels, you get the complete image. So for an RGB image, this input number of channels would be 3, because your image would would be a 3-dimensional tensor rather than just a 2D image, because there would be 3 channels associated with each layer. Now this output channel is up to you what you want to decide. Because we are working with MNIST dataset, which has 10 classes, I chose this to be something close to 10. Okay, so once you apply once you apply this convolution, it will pop out an image. It would again pop out a tensor, which is the size of your image, but then would have 12 such channels of the image. So the image would be, it's again a 3-dimensional tensor where it would have the length and breadth, but it will also have a width. So essentially, this determines the number of filters you use in your first convolution layer. So this would be this would mean that you have 12 filters that will act on the image, and then it will provide a feature map. That it will provide 12 different feature maps of the image, and so each of the convolutions will be of size 3 by 3. Okay, and they will after a kernel is applied on a subset of an image, it will take a stride of 1, and then we'll have a padding of 1 around the image when we are processing the input. Now, the more the output channels you have, the more is the number of weights your model, your CNN is trying to estimate. So again, the more channels you decide to have, the more data you would end up needing for training. So so I think 12 is a good number here. So we'll see how it performs. Now, once you have this convolution layer, that takes care of the first part of the process, the feature extraction part, and then you apply an activation to non-linearly transform whatever you have learned in the first step. Now, again, I guess you can ignore dropout for now. It's a regularization technique that with a certain probability just sets some features of your vector, your image to 0, and that helps the model to generalize better, because otherwise the models, your different weights can form local correlations, and that helps to drop those correlations and prevent the model from learning those correlations. So for now, yeah, I've just set it to a constant 0.25, but you can feel free to ignore this. Now, once you apply the activation on the extracted feature maps, then you do something called as the pooling, which is a dimensional reduction of your original image. Okay. Now, what does this say? Pooling. So pooling reduces the image dimension. So again, if you have, say, so suppose after applying the convolution, you had a feature map that is 6 by 6. Then what pooling does is it takes, so here we have some parameters that describe the pooling. It says a kernel size of 2 by 2 and a stride of 2. So it takes every 2 by 2 subset of the image and it averages. So, okay, not averages. Here we are using max pooling. So it takes the maximum of the value in that 2 by 2 cell. And then it now creates an output, a reduced output. So this is 6 by 6, right? So it creates a 3 by 3 output. So it takes this cell and then it takes the maximum of these 4 pixels and it assigns to the first cell. And then it takes the next 2 pixels, 2 by 2 pixels, and then it assigns the maximum of that to this layer. And then so on, this grid, sorry, and then so on. So the stride here determines how much step it takes to determine the next maximum pixel. So right now it starts with this image and it takes this index, and then it strides 2. So it starts with the, rather than starting with the first one, rather than starting with the second one, it starts with 1 plus 3. So it takes a step of 2, and then it takes the maximum of the next cell, and so on. So you end up with a 3 by 3 pooling layer, which represents a reduced dimension representation of your feature map. Okay, so this is the first step. Now this defines the first convolution layer essentially, and then if you decide to have more convolution layers, like we have here, we have 2 layers. So then the second layer again could be defined similarly. So of importance is the arguments that you pass here. So because your first convolution layer was had 1 input channel, because we were working with a grayscale image here, and then 12 output channels, this same number of output channels would be used to create the next convolution layer. Okay, and then you can determine how many output channels you want for this layer. I have set this to 16. You can try out different numbers as well. I just wanted something close to 12, but not excessively large. I'm using the same kernel size again, but I also have a Jupyter notebook in the code HTML, where I have in the HTML of Jupyter notebooks, where I have 2 different Jupyter notebooks where I have a larger kernel size. And then you can kind of see what we're trying to interpret the layers later, and you can see what effect it has, what effect using a larger kernel size has on your outputs, and what kind of filters you get. So again, I'm using a stride of 1 and a padding of 1. So this preserves the. So if you use the formula above, this will preserve the geometry of your image. So if your image was 28 by 28 before, it will output a 28 by 28 image later for the first layer. But because now we have pooled we have a pooling layer above, right? So that, as we saw, it reduces the dimension of the image by a factor of 2. So this layer's input images would be size 14 by 14. Okay. Now again, we apply an activation which introduces non-linearity into our problem, and then we have a pooling layer which again is identical to the previous pooling layer. So it reduces the image further by a factor 2 in each dimension. So your image is now, your distorted, your processed image features maps are now size 7 by 7. Okay. Now you feed them into a ANN. So any questions so far? Yeah. What about it? So this convolution layer generates the filters. So the kernel size here, this determines the size of the filters, and then this output channel determines how many filters I have. Where I get the filters from? There are 12 filters. Oh, so as I said, we don't have them defined already. The objective is to determine the optimal filters. So once your training is over, you will get the filters that best allow you to predict the output. I mean, it happens automatically. So the filters itself are weights of the model. So when you make an update through backpropagation, it updates the weights of the filter, like the contents of the filter. And then, sorry, how much time do I? Yeah. Not really. No, you can add an isotropy. It could be different. That's why it's a two tuple. Good. It could. Yeah. Yes, you can. Yeah, you have all the freedom there. Yeah. Okay, so now comes the step when we distort the image and we reshape the image. So we are essentially reshaping the image, but after processing it and extracting features from the image. Now that we have done that through convolution and pooling, we define our hidden layer, which would be, again, sorry, we have 7 to 10 minutes. That's good. So we have, so now, as I said, our initial image was size 28 by 28, but then each pooling layer reduces it by a factor of 2. So then now our initial, our feature map after 2 pooling layers is of size 7 by 7, and we are reduced, and it has 16 channels because this convolution layer, after passing the reduced image through 16 channels, produces 16 such images. Okay, so overall you have 16 copies of a 7 by 7 image. So you have overall 16 times 7 times 7 pixels to send into the artificial neural net, and that's denoted here. Okay, 16 times 7 by 7, and then you can choose number of output classes. I've chosen 32 here. I think 10 to 20 should also work pretty well in this case. And then you introduce the nonlinearity as you do in ANNs, and then finally you have the output layer that makes the prediction. So it takes the input from this hidden node. So there's 32 activations in that node, and then there's 10 classes which are defined here, digits 0 to 9. Okay. Now that pretty much defines your convolution neural net. You have the convolutions, you have the activations, you have the pooling, and then you have multiple such units, which then lead you to entering your image into an ANN, which, again, you can have multiple hidden nodes in your ANN. It's your choice. But for this case, 1 works pretty well. So I started with 1 and it generated a pretty good prediction scale. So now the forward function is similar to what we had yesterday. We have the convolution layer that sends your different filtered images, different feature maps to the activation, which then, again, ignore this, is treated as an identity function. And then you have the pooling layer, which reduces the dimension of y. And then you pass it through the second layer. So I've compounded the functions here just to shorten the code. And then you reshape it into a vector, the image into a vector, and then you apply the first hidden, you pass it through the first hidden node of the ANN, and then finally you take the output. So that's your forward function. Simple enough, right? And then you initialize your model as an object of the CNN class. You set the optimizer just as you did yesterday. We choose a reasonable learning rate, and we choose a cross entropy loss as a loss of choice for this problem. Okay, so now this training function is same as before. It's pretty much identical as before. We don't have to go through this today. Okay, so we'll just execute it, and we train this model. We train the CNN for 10 epochs. Now, does anyone want to place a bet if it will cross 99? Sometimes it does, sometimes doesn't. It doesn't, someone said. Okay, let's run it and see what happens. So again, we have used a very simple data set here. That's MNIST, 28 by 28 pixels. So you can't really do a lot with this, but this is a benchmarking data set. And if your model performs well on this data set, it's quite likely that it will perform on more complex data sets as well. You might have to make some changes. But so you see, if you remember from yesterday, after optimizing everything using the best optimizer for our problem, we achieved or asymptoted at a prediction scale of 97.5. And however, in this case, we started like the first epoch itself delivered a prediction scale of 97.53, which is as good as the final prediction scale of our ANN yesterday. And it's increasing further. Now, as I mentioned, the state-of-the-art digit recognizers have a prediction scale of 99.91% or something, so which is pretty impressive. We may not reach that today, but as you can see, we are getting close, and that's probably because that's most likely because we have processed our input differently in a more intuitive way, as you know, just how we look at any images, at images in general. So you see, we are reaching 99% almost. But and again, so you notice that from epoch 5 to 6, the error has gone. The prediction scale has suddenly dropped a bit, right? And that's totally fine, because what might be essentially happening is the algorithm is exploring the loss space as a function of different weights, right? It's possible that it started from this place. Let's. So this is your global optimum, but this is your local optimum, right? So it's possible that it first reached somewhere here, and then because of the momentum and all the different varying learning rates your Adam optimizer had, it got it got transported, or it got updated to this more optimum value. Or no, sorry. So sorry. So maybe it's okay. Let's no. So say this is your optimum value. Okay. So suppose it started from here, and then it was probably updated to this value. So this is your W1. This is a W2, and then due to a large learning rate or something, it was directly updated from this W2 to this W3, which you can see is not the global optimum. But then as you train it further, no, I'm not saying it clearly. Okay, no. So sorry. So yeah, let's. So suppose after a couple of steps, it reaches at this rate, and then it gets updated to, or we don't even need a second value. Suppose it, so it's reaching the global optimum step by step, but it gets transported to say this side of the valley of the optimum, and then suppose the next step is this. So even though it's in the valley and it will eventually get here, you see a minor update or reduction in your prediction scale. And then in the next step, once it realizes that it has crossed the valley, it again tries to push the weights in this direction. and so on. Okay, so these minor changes or minor reduction in the prediction skills should not matter in the long run. And now, as you can see, okay, it did not reach 99. So because we are using batch gradient, mini batch gradient descent, for some instances it does, for some it doesn't. But it's pretty cool, right? I mean, it reaches a maximum skill of almost 99. And if you look at the error plot again, and you compare the training loss with the test loss, you notice that your training loss decreases monotonically, but then your test loss decreases up to epoch 5 or so, but then above that, after that, it tends to increase again, right? Which tends to suggest that we are probably overtraining our model beyond this point. So this is probably a good stopping point for your training. And see, epoch 5 is exactly when we got the most prediction skill as well. So now let's just look what our model learned real quick. So this cell generates whatever predictions, it visualizes whatever predictions it got wrong, the CNN got wrong. Okay, so for this particular mini batch, it got 2 wrong predictions. First one was an 8, which is predicted as 0, but as we can see it, it's an 8. And then again, this one, it predicted as 5, but it actually is 9. And then similarly, it's predicting this as 0. So, and then predicting this as 5. So 7. So, I mean, at least in this case, it's easy to sort of understand why it would have thought it is a 7 and not a 5. This is sort of a bad guess, I think. So again, this could be, you know, if you think this is something really shouldn't be happening. Or for instance, in this case, yeah, we can see that it's probably a 2 because we have this protrusion here that usually is associated with the 2. But because it probably did not focus there, it focused more on this loop with a empty space in the middle, it thought it's a 0. So some of these could be resolved by adjusting the kernel size and looking at the feature maps as to, just to determine the scale of information it's considering when creating the feature map. And again, so if you have, suppose, a vorticity map or something, right? Or if you're working with vortex-vortex interactions where you have a lot of vortices in your image of different sizes. So again, it would be good to use kernel sizes of different sizes and not just restrict to a 3x3 kernel because your vortices could be of different sizes. Okay, and you want to spot those different scale vortices efficiently. So using just a large filter will just average out the information a lot to the extent that the small scale vortices would not be captured very efficiently. So now let's look at the feature maps. And okay, first let's look at the filters. Okay, now when we so you can actually get the filters using this command here, like the model and the layer name. It has the following weights, and then because you want to plot it using matplotlib, which takes numpy arrays as input, you will have to detach it from tensor from torch to numpy. Okay, so that you can pass it as arrays to plotting functions. And then if you plot different filters which are of size 3x3 as defined, you see that it's difficult to interpret these filters. They're not as simple as our filters that we looked at before, like the Pruitt filter or the Sobel filter or the Laplacian filter. These are more complicated. But then if you look at the impact, like the effects of sending an input through these, it's not that bad. So let's take a random input, okay, and then pass these through filters. So this is our input, and then remember we had 2 convolution maps, right? And then in each convolution layer we had we had 2 convolution layers, and then for each convolution layer we had like 12 filters for the first one and then 16 for the next one. So I'm only plotting the first 3 here. So once you pass this through the first convolution layer, it somehow filters the 3, and then it highlights certain features of 3, like this horizontal bar above, this curve below, and then depending on what layer it is, different features are highlighted in the feature map. So here it just pretty much highlights all of 3. But then as you go deeper and deeper into the deeper layers, you notice that the information it retains or the shape of the input it retains gets really blurry. So at this point, it's just a very blurred version of 3, and it might as well be an 8, right? And then similarly for 5, it retains the overall shape, but then it's a much more pixelated version of the input, and so on. Now again, the larger your filter size, you see the more interpretable it gets. So just for instance, if I do this, and then so this is a filter. I think this is a 15 by 15 filter. Okay. Now here you can actually see some pattern. At least it's not just a collection of pixels, but you see that there are these strokes. There are different loops. And then you have certain coherent loops, at least, where you have negatives and then you have positives, and that corresponds to kind of this corresponds to a gradient, this direction. So you can at least interpret them more so than you can interpret a 3 by 3 filter. So and likewise say for this, your second filter was larger. So here it creates I'm just trying to interpret them, but it creates these alternate bands, and they somehow suggest that this is associated with a stroke here, with an empty space here, and then another stroke here, and so on, and then this empty space around it. So and close this. So I mean that's pretty much that's pretty much how you apply or create your own CNNs in PyTorch. But as I said, it's a toy problem. I would highly encourage you to take up a more advanced problem with, or a more, there are many other data sets like for animals, for food, for apparels. Apply them, and then they have more features than these 0 to 9 numbers. So you should just train your model on that data set, and then see what kind of feature maps it generates, and then how you can interpret those, and then what impact you can have by using different filter sizes, and so on. So that kind of concludes our coding part of the lectures. But I would encourage you to kind of go back and having learned how to create a neural net, try to create your own recurrent neural net, for example. I mean, recurrent neural nets are used for time series forecasting and sequence modeling, and constructing them, writing them in PyTorch should be easy. As per the data set, you can use a simple Lorenz 96 model or so, and then just integrate it using your numerical temporal integrator of choice, and create the synthetic data, and then use that data to develop the forecaster using RNNs. And I think that would be a nice exercise, because it's a different kind of neural net, but it essentially uses these building blocks. It uses multiple cells of ANNs lined up, one adjacent to each other. So I think if you can implement that, I think that would be a fun exercise, and I will reinforce the concepts you have learned here. But yeah, that's pretty much it. Yeah. Yeah. Sorry?
You said that when you were testing this, at 50 epoch, you had the maximum. That's why the error was showing over here.
No. I didn't say that. That it has to be the minimum at wherever the prediction skill is highest.
Like last coinciding at this point. But in my case, the maximum was at 98.95, 8 epoch. Which was here.
Yeah.
They should be stopped.
Again, the loss curve, the shape of the curve should be the suggesting factor here. I would suggest stop at this point.
But the best outcomes are coming at 7 and 8.
Yeah. Okay. So more generally, there's this algorithm called early stopping. So what you do there is you track the error for a certain number of steps, and then whenever you have the minimum in your error, you record the weights.
Okay.
And then as if your error does not, your validation loss does not decrease for say 10 or 20 epochs, then you just stop your algorithm. So, that would be a more accurate way to kind of decide the optimal weights.
You're saying you should stop at 5 itself.
In this case, yeah.
Even though the outcomes are coming at 78, the best.
Okay, so that's 8.
98.95 is coming, 98.91 is coming over here.
Oh, yeah, sorry. So, yeah, you should stop at epoch 9.
Epoch
9, yeah, wherever the maximum is.
Okay. So this is this point.
Yeah. So if you implement early stopping, then that would record the weights associated with this time step. And then you can, during inference, you can use those weights. Any questions? Yeah.
So you have a striding number for passing through that image with your kernel matrix. So that number is for passing horizontally. Is there a concept of passing vertically also?
I think, again, stride is a tuple. Yeah, so yeah, I have this here. So stride is a tuple as well. Yeah, you can just use that. Yeah.
So if it is not defined, it must take some default value.
I think the default is 1. And if you just add one number, it would just use that for every dimension.
Okay.
Yes.
Better if you use average. But is there some other reason why we are using the max function rather an average function?
Intuitively, max should work better because if you're trying to locate small scale features in the image, then the maximum function would be better because the average function would just average over the whole grid cell, while the maximum function would usually be associated with the location of that small scale feature, while the average function would smear it out. Yeah. Again, it could be possible that for some problems average works better. I mean, I don't think there is any general rule.
Hello, sir. Sir, my question is to optimize that, to know the small scale features well. Should we always use the kernel size as small as possible?
For small scale features, yes. But if you have features of different sizes, then I would recommend using bigger. So I would recommend that for the first layer, you use a small kernel size. And then as you go deeper and deeper, you use a bigger kernel size because your small scale features would either way be diffused out or averaged out during the first layers. So then, but your large scale features of the image, like a mountain, for instance, will be preserved into the deeper layers as well.
Yes, sir. And choosing that filter, should we do like that? That there may be some standard filters for some standard pictures for some analysis, and we should improve that mathematical filters by just training them. That we should say that they start from this filter and just improve this model.
Easier said than done, right? I mean, an image is complex.
Basically, these filters are just a mathematical operator which are restricting the some of the features to go further, isn't it?
Sorry, I didn't get that.
These filters are some mathematical operations which are restricting that some of the previous functions, previous features to proceed further in the image.
Yes. Yeah.
Then there must be some standard mathematical filters which can apply to and we can improve in that training model with to that mathematical filter during entire training.
You mean start with an intuitive filter and then just let the model build on that?
Yeah.
Interesting. Yeah, I don't see why not. Yeah, I think that's.
I'm still learning this. I don't know. That's why.
Yeah, I have not heard of this, but I don't see anything wrong with this idea. It's possible you'll have to scale the filters appropriately. Otherwise, you will just, there's a potential of model blow up. But if you scale them properly, then I think it should. But again, determining a filter that works for all images in general is tricky.
Very complex.
So like that slanting operator, for instance, you actually need to have a straight line for that to always work, right? So,
Thank you, sir.
say a random perturbation around it. Yeah, something like that. It could speed up model training. Yeah, possibly.
Okay, if no more questions, let's go for tea, coffee, and then there's a poster session outside, which I think officially is supposed to begin at 2:45. Oh, it's 2:45. Okay, and that will go on till roughly 4, right? So let's reconvene 5 minutes before 4 for the next one. Thanks, Aman.
Yeah, thank you. Oh, sorry, there's a question in the chat. It is possible. So just to quickly answer your question, it is, and that process is called upscaling. So just like we use a max pooling layer, you can, you can use an upscaling layer as well to introduce, to expand the dimension of your image, and people do that quite frequently. Yeah, but again, you will be, interpolating when you actually do that. Okay.